Italy Whiskey 5 Echo Kilo Radio Mobile from Whiskey United 2 Delta.
United 2 Delta, Italy Whiskey 5 Echo Kilo Radio Mobile. The name Aldo, like Alpha Lima Delta Oscar. Aldo is the name. Your signal 55. Excuse me. 55 your signal is sent to Italy. My location is 200 meter north of Rome. Repeat the 55 your signal in the AM mode. Whiskey United 2 Delta. Whiskey 5 Echo Kilo Radio Mobile.
Very good, Aldo. Good copy. So a little holiday bonus video concerning the 10-meter AM Junkbox Rig and trying to improve the modulation a little bit. Somewhere around 30% modulation, distortion becomes evident. There's some kinks in the modulated waveform. So there definitely is some distortion going on with the tetrode modulation system we're using, which is a very simple resistor feeding the screen off the top of the modulation transformer. Now, with real speech and a real microphone, it doesn't really show up that much on the air. People think the audio is okay. They think it's good quality. But we know there is distortion. So what I'd like to explore in this video is possibly some other methods of modulating a tetrode. And one of them is called self-modulation. Self-modulation. And another is called ratio modulation, where part of the feed to the screen is modulated and part of the feed to the screen is fixed voltage below the modulation transformer. We're going to investigate some of these different types of feeding the tetrode tube for AM modulation. So let's take a look at this test setup that I am using to do my modulation testing. First of all, I'll call your attention to a new control. It's a transmit on-off switch, and since this is a Junkbox rig, we can drill holes and mount things anywhere we want. That's the nice thing about something like this. Now, to feed audio into the transmitter, I'm coming out of a Heathkit generator. My goal was to have the gain control at the exact same spot that you use for the regular microphone. And I have a one-to-one transformer. I didn't want to create a ground loop between the generator and the transmitter. There's also a 10-to-1 voltage divider there. It's just a 10K resistor and a 1K. It's a rough 10-to-1 divider. And that brings it down to mic level. And with the generator set at a fairly low level, like 100 millivolts type output, it gives me the mic level that I'm looking for. So if I flick that toggle switch, anyway, here we are. You know, it's 30 or 40% modulation, and it looks pretty good. We're getting pretty good modulation. But if I start to increase the, you can see as we approach 100% modulation, there's bumps in here. See these bumps? That's distortion, guys. Now, it turns out when you're, talking on the microphone, that stuff doesn't really show up in something that you can hear on the air too clearly. I'm sure that critical ear could hear it. But for the most part, people think, oh, you've got pretty good audio. It's pretty good modulation. But we know that it is nonlinear. Once we get over 30 or 40% modulation, it definitely goes nonlinear. So let's see what we can do to clean that up.
So let's look at some of the typical culprits when you can't quite get 100% modulation. The first one is obvious. It's insufficient modulating power. It's a normal issue, but not here. A pair of 6L6s should easily be able to modulate our 6146 at this low RF power level. I was starting to suspect that the one-to-one transformer that I got surplus was not as ideal as I thought it was. The plate-to-plate impedance of a pair of 6L6s at 450 volts is closer to 10K ohms plate-to-plate, not the 5K I had predicted. So matching the modulator to the final, it looks like I had a mismatch problem right out of the box. The modulator grid swing from the phase shifter That's fine. And the 6146 screen resistors, I seem to be able to vary them between 20K and 33K. That all seemed to work okay too. One effect that quickly improved the situation was simply adding resting current to the 6L6 modulators during transmit. So just upping the resting current to around 60 milliamps instead of the 30 milliamps that I had set. This, of course, lowers the plate-to-plate impedance of the 6L6s, and that certainly improves the match. But the problem turned out to be worse than that. The requirement for heavy resting current, really closer to Class A push-pull, gave away the real issue. Metering showed that during transmit, the screen voltage of the modulators sagged from 368 volts to 265 volts, a 100 volt drop on the screens. And of course this caused the resting current to drop from that 30 milliamps I'd previously set to something around 12 to 15 milliamps. The 6L6 tubes were running much cooler during transmit than in standby. That's another symptom that something was wrong with the biasing. Simply turning up the bias was going to create another issue that was quite dangerous. All fine during transmit with the higher resting current, but when I went to receive, the voltage on the screen would then soar and the resting current would go way up into the danger dissipation zone for 6L6s. Of course, the normal solution for something like this is to simply regulate the screen. Regulate the screen voltage to, say, 250 volts or 300 volts. But fortunately, there was a simpler solution. The audio amplifier only needs to be active during transmit, so it's different than your hi-fi. It only needs to be active when we're actually modulating. So why not switch or clamp the screen to ground during receive? So all I had to do was feed the screen off the switched driver power supply. So I moved a wire, and I added a 200K pull-down bleeder on the screens just to be safe. And this got me cooler 6L6s when I'm in receive, and a pretty picture on the scope. The modulation started to look like it was getting close to 100%, all for the price of a moved wire and a trade on a resistor.
Okay, with the fix in place, the 6L6s are all warmed up and I'm touching them. And believe me, if I can touch the side of a 6L6, it's cool. So it's in standby. I'm going to go to transmit, and it looks like we have a good carrier. And I'm going to introduce some modulation from my generator into the transformer and the voltage divider that I'm using as a guard against ground loops. So you will agree this is starting to look like what you expect to see with an AM transmitter. Pretty good looking envelope. We can go beyond 100% into full clipping, both negative and positive. Next I'm going to connect for the trapezoidal pattern. We do that with the XY on the scope. I've got a tap off the modulator transformer voltage divider, because we know we have hundreds of volts coming out of the modulator. We need to bring that down so we can bring it into the x-axis on the scope, and of course the y-axis is the RF. So let's set up for trapezoid. So when doing an XY type of display, like the trapezoid display we're going to be doing, basically get a dot in the middle of the screen or close to the middle of the screen, and you'll be adjusting the horizontal and vertical axis to give you a good picture. So let's turn on the carrier, and as you can see, the carrier looks like a vertical line, and now we will start to add modulation, and we should start to fill out the pattern. Okay, we're starting to get the trapezoid. Not too bad. That's showing 100% modulation. Bring up the intensity a little bit. A little bit of distortion around 0, but that's basically 100% modulation. there's not a lot of distortion, a little bit of phase distortion showing here. I can try to focus this a little better, but that's a nice trap pattern. We know we're getting good modulation now. And this is the screen grid method, remember, where the screen grid is being fed up above the modulation transformer. And we have a 20 to 33K type resistor up there. I can't remember what I've got in there right now. I use 27K, I think. And this is a good starting point. And we've got good quality modulation now, probably much better than what I had on the air the last 3 weeks, that's for sure. But nobody seemed to mind it too much. So next we will try a self-modulation system. And I want to start with the choke system that connects below the modulation transformer. So this is self-modulation using a choke. Now because that voltage is so high, I will be using a series resistor on the bottom of the choke. Basically for safety, just to make sure that the DC potential on the screen is low enough to be safe. That could be maybe a 10K resistor, something like that. I'll put in series with the choke. Maybe something smaller, but depends on what voltage we have there statically with just the carrier, and I'll adjust that resistor accordingly. Let's see what we can do with self-modulation.
So remember that the reason I'm covering tetrode high-level AM modulation is not because my Junkbox rig needs all of this critical distortion measurement. It's because tetrodes and pentodes are not perfect square law devices compared to triodes, for instance. Triodes are far easier to modulate, and you get almost distortion-free results when you modulate a triode. It's a little trickier with pentodes and tetrodes. With high-level plate modulation in tetrodes and pentodes, the screen grid typically needs between 50 and 60% for linear 100% modulated AM. A number of common commercial AM transmitters that we all know, such as the Johnson Ranger and Heath Apache, connect the screen dropping resistor to the modulated B+ above the modulation transformer for high-level AM. Just exactly what we did. With some care, they managed to get pretty good looking AM. Usually when this simple resistor above method is done, the screen grid actually becomes overmodulated. And you usually will see a glitch at about 85% negative modulation and a pinch off below that. Yes, we are seeing that in the trap pattern that I put up. This was a common defect. You can see it in the ARRL AM trapezoid patterns in many of the handbooks even. But the system is simple and commonly employed in designs. So many manufactured AM transmitters and transceivers continued to use this method. It does work, but remember, you will get some distortion. Okay, we need a little bit of folklore and sage advice on this subject. First, let's tap into IMAC's care and feeding of power grid tubes. In anode and screen modulation, it's necessary to introduce not only amplitude modulation of the anode voltage, they're talking about the plate, but also to develop 70 to 100% amplitude modulation on the screen voltage to get 100% carrier modulation. Modulation of the screen voltage can be developed in one of the three following ways. A. By supplying the screen voltage through a dropping resistor connected to the unmodulated DC plate supply. Self-modulation of the screen works because the screen current varies with anode voltage. The screen system, in effect, becomes a constant current supply for the screen grid. As the plate modulator pushes anode voltage higher, the screen current decreases. Decreased screen current causes the screen voltage to increase. This system, when a resistor is used, normally requires the screen supply to be about 50% higher than required. With a screen choke, however, the screen supply voltage can be equal to the desired screen operating voltage. For a 6146 with a resistor method of supplying constant current, the screen source should be at least 300 volts. Screen voltage is often sourced from the anode or plate supply line. When a low voltage fixed screen supply is used, a modulation choke is placed in series with the supply. In the case of voice modulation, you're going to need about a 5 to 10 Henry choke. The third method, or C, a third winding on the modulation transformer called a tertiary winding, designed to develop the required screen modulation voltage. You're not going to find too many of those around, guys. If the dropping resistor comes from unmodulated B+, the glitch goes away and the modulation is more linear. You could put a choke in series with the resistor, but it isn't necessary because the resistor is a high enough impedance to let the screen modulate it as it wishes to. That's from Bacon, WA3WDR. Dean, WA1KNX, goes a little bit further, and he says that you actually need a combination of two dropping resistors and possibly a capacitor, one going to the unmodulated B+, and one going to the modulated B+. This gives a slight boost to the modulation on the screen, and it produces the most linear modulation of all. Continuing, and take it easy on me, we're pretty far in the weeds now. This is from Bruce, W2XR. My suggestion is to go with the screen reactor to the unmodulated supply. Once you know the impedance presented by the screen, based upon the screen voltage and screen current, you can easily calculate the screen impedance. The screen current should be determined at the operating point of the modulated amplifier when it's loaded to the desired plate current, as the loading has a very pronounced effect on the screen current. Increased loading equals reduced screen current. A good rule of thumb for the required inductance is about 10 henries of inductance for every 1000 ohms of screen impedance. This will enable the final amplifier to fully modulate at very low frequencies like 40 Hz. Obviously, the current rating for the reactor must be based on the screen current drawn. Another point to consider is keeping the screen reactor above ground potential. This minimizes the effect of the reactor to shunt high frequencies to ground, based upon the distributed capacitance of the winding or core to ground within the reactor. A couple of ceramic standoffs would do the trick. The -3 dB point for low frequency roll-off based on the screen reactor inductance can easily be calculated using the simple formula for inductive reactance. Further to my previous post on the subject, if you do elect to go with the screen reactor approach, you will need a separate power supply for the screen. For a small 40-watt rig, the added complexity of this additional supply may not be justifiable. And a follow-up from Bacon. Screen self-modulation works very well. However, it's just slightly low, and a little assistance improves linearity a bit more. WA1KNX Dean found that a combination of two dropping resistors was best, one going to the unmodulated B+, and one going to the modulated B+. This gives a slight boost to the modulation on the screen and produces the most linear modulation of all. And from Dean. Using the trapezoid scope pattern for verification, I changed the screen circuit to a network where part of the screen voltage is from the fixed plate supply and the other parts from the normal plate dropping resistor. This achieved the goal of more screen on the negative swing and less on the positive swing, and resulted in a perfect waveform, except for a small bump that was still present near the cutoff or the bottom of the modulation swing. I determined that increasing the grid drive from 2.5 milliamps per tube to 3 milliamps removed the bump and left an exquisitely perfect modulated waveform. With proper voltages now on the final, another overlooked source of distortion is the RC time constant set up by the screen dropping resistors and their bypass caps, which can cause a phase difference between the plate and screen modulation signals on higher audio frequencies. A technique used to eliminate this was to place a proportionally valued capacitor across the plate to screen dropping resistor, thus canceling the effect of the screen bypass capacitor. Distortion from this can readily be seen as a loop effect on the sides of the trapezoid pattern. In short, for the 6146 I recommend the following. 3 milliamps per tube for grid drive. Derive 60% of the screen voltage from the plate dropping resistor and 40% from the plate supply. Place a capacitor of approximately the same value across the plate to screen dropping resistor. So K1JJ Tom, he does comment. He says, interesting information. Yes, I remember pondering Dean's dual method. That does make a lot of sense. Why? Because who's to say that by adding a choke either to the B plus or modulated B plus alone, that's going to produce a perfect mix of additional voltage swing to the screen. For maximum linearity, you would think there is a sweet spot, and tweaking could find the optimum level.
Okay, my first attempt at self-modulation. I've simply moved the screen resistor from the modulated to the unmodulated side of the transformer. Let's go into transmit, and let's add some modulation. Actually looks pretty darn good down below there, but we absolutely have some non-linearity around the curve. This thing looks pretty funny. Let me play with the tuning a little bit. Yeah, it's definitely smooth but non-linear, and a little bit of phase distortion showing up as well. But that's self-modulation. That screen resistor is not attached to the modulated side of the transformer. It's going straight to the B+. Okay, next I have inserted a 20 Henry choke, 2-0, in series with the screen resistor of about 20K, and it's on top of the resistor attached to the screen grid. Screen grid bypass, by the way, is a 2200 picofarad capacitor, 0.0022. Increasing the audio, let's see how it modulates. Again, this is self-modulation, this time with a choke. Yeah, the pattern has straightened out a little bit. I can't say it's much better. Playing with loading affects things a little bit, but it doesn't look too bad. So I want to measure the voltage on the screen grid. .205 volts. So that's identical to what we had before, but now we have the inductor, the choke installed, and of course it has a very low resistance. It's around 50 ohms. So the choke did help to straighten out the linearity a little bit, and we still have a very good looking low end. So before I leave the choke idea, I reduced the value of the series resistor to 5.6K from 20K, just to give that screen grid more voltage. And let's see what that does with the choke. Okay, let's add some modulation. Again, we have the 20 Henry choke with a 5.6K 2-watt resistor. Okay. That seemed to linearize the pattern quite a bit. It's looking pretty good. Just a little bit of droop at the very top, but that's a good looking pattern right there. One further thing I want to try a bypass capacitor, a large value electrolytic at the top of the 5.6K in order to make a very stable screen grid supply for the choke. Let's see where we are at that point in voltage right now. Remember, we were at 200 volts with a 20K resistor. 281. So 281 volts on the screen is probably a better place to be, since we only have a 450 volt power supply for the plate. So this is probably a better setup. Let's see what a cap would do. Okay, I've clip leaded in 100 microfarads of capacitance from the top of the 5.6K to ground. That's going to make a stiff screen voltage supply. It also has a little bit of a bleed on it for stability. This should give us a much more stable 280 volts. Okay. but a pretty good looking pattern, except at the very, very top, which is the 100% positive swing. Just wanted to try that before we went on to the 2 resistor ratio method. Okay, I now have the ratioed resistors in, and I have a way to connect the capacitor in and out, so you can kind of see some of the effects. So let's go into transmit. Hope you can see that. I'm going to put the capacitor in and out now. Now this is the compensation capacitor across the modulated resistor. Can you see that? I'm using a insulated tweaking tool. See how that fixes that end? Gives a little more modulation on the downward. Now let's look at the normal swept waveform and take a look at the effect of the compensation capacitor. I see distortion there, no doubt about it. Let's put in the compensation cap. Everybody see that? That does help things. Fills out the waveform. So again, if you play with these values, you're going to be able to improve the modulation to the point where it's getting close to perfect. But it depends on your conditions, your voltages. I'm operating at oddball, very low voltages. The 6146, of course, would be much happier at 600 or 750 volts. Of course, the conditions would be totally different. The calculations would be different. Just wanted to show you the effect of some of these ideas on the waveform. A lot of you were afraid that I was going to get some kind of a high voltage shock or a lethal incident in all the work I've done on the Junkbox Rig. But I can report that I've gotten through the whole video series without one incident. And I'm going to do the satisfaction that you guys have been looking forward to, which is putting the bottom cover on the radio. Once the bottom cover is on, the radio is finished, it's ready to get its feet and be put on the shelf for use in the ham shack. You might wonder what I was using for that choke during the experiments. Here it is. This is a nice 20 Henry 70 milliamp choke. But I wanted to be able to use a choke that was adequate for dispelling the naysayers that always say, hey, you haven't got enough Henrys there for audio. Well, there was enough Henrys for audio here. So I hope you've enjoyed this series on the 10 meter AM Junkbox Rig.